Hello, Tensor friends. Yesterday I posted a video where we looked at the change in a position vector with respect to an arc length. And what we did was derive using the definition of a derivative. We derived this unit tangent vector, which we're going to use later on to our study of curvature in Riemannian geometry. So I just wanted to introduce it. But in doing so, we used a circle because it's easy, and I just simply I stated that the arc length is r times the change in the theta, and this violates the whole point of tensor calculus, and I know better than that. So let's clean that up. The point of tensor calculus is to generalize everything, so it's an invariant, and we can use it in any coordinate the system. So I broke a fundamental rule here, and I got punished. Okay, so for any function, we can use the arc length of formula, which comes from this, and we've seen this before. So this is the infinitesimal invariant arc length equation, which says that the square of the arc length, the square of the change of the arc length is equal to the metric tensor times the infinitesimals of the coordinates you're working in. Okay. Now, yesterday, since we're using a circle, we were working in polar the coordinates. So the metric tensor in the polar the coordinates is given as this. So this is er dot er, and this is e theta dot e theta, and we've seen this before. Okay, so using this equation, so GRR is 1, and that'd just be dr, so dr squared. And G theta theta is r squared, and that'd be d theta times d theta. So here is our called the line element. Everybody calls this the line element. I'm not sure why. Okay, so how can we get the arc length out of this? Well, let's take the square root of both sides. And remember yesterday what we were doing. I think it was yesterday. It doesn't matter. We had a position vector, and we added a small amount of change to that position, the vector, and we needed to know this arc length to do our equation, right? Because that was in the definition of a derivative. So we needed the change in of these two vectors to calculate that arc length. So we need the change in this equation with respect to the angle. So we can take the derivative of both sides. All right, so what is dr d theta? Well, r is a constant. We're not changing r here, right? We're just changing the angle. So this is 0. And d theta is obviously 1. So we're just left with d theta, ds d theta is equal square root of r squared, which is obviously r. We get ds equal r d theta, take d theta to the other side rather, integrate it, and we get s equals r times the change in the theta. So this would be evaluated, this integral will be evaluated from wherever these two angles are. All right, so it's the same equation we used yesterday. It's just that in tensor calculus, you always want to start with the generalized formula, right? So that's the difference between tensor calculus and vector calculus. Is in vector calculus you would just use this. So, okay, now let's use this in a totally different the format just to hammer home how it's used. Okay, let's take any function. I just took a parabola, y equals x squared. Okay, so the line element, the formula ds squared is equal to, once again, the metric tensor times the product of the coordinates. All right, now what is the metric tensor in Cartesian coordinate? It's the identity matrix, right? So it's 1 times dx, dx squared, 1 times dy times dy, which is dy squared, okay? Now, what do we want to do in this equation? Well, first of all, let's take the square root of both sides. In this equation, we have a parabola. We did our position, the vector. This is our position vector. We added a little bit of increment to it to form a new vector here, right? So this is part of our definition of a derivative. So it'd be RH minus R divided by this arc length, the change in this arc length, all right? So we want to know the change in this coordinate system. We want to know the change in X, right? So we're going out another X away from this one to form this new vector, all right? So we would Take the derivative of both sides with respect to x. Dx dx is just 1. Now dy dx. Now what is dy dx? Well, we have an equation for y. It's x squared. So what's dy dx? It's 2x. Put that back in right there, and we get this equation. Now what do? Well, we integrate both sides. So we move the dx over here. We run the interval from 1 to 1.5, which is where I made it. So it's 1x, and then I go over 1.5, and that's where this one is. So I need that piece of arc. Okay? So it turns out the integral of this is a real hard integral. This is some hyperbolic trig identity function thing. I had to look it up. Okay? And the answer is the arc length of 1.35. Okay? So the whole point of this brief video is just I should always start with the generalized expression for whatever it is we're working on, because we're studying tensor calculus on our way to Riemannian geometry. That's the whole point of this. All right, thanks for watching.